Okay, so it's going to be an introduction to organic chemistry. It should help you out with a few things. Also help you if you move on with this, or, or do some biology, or A&P. So that word organic has sort of been co-opted by the food industry. I don't know if you guys know who Alice Waters is, but she kind of stole that word a long time ago because she liked it. She's the person who probably is the most famous person as far as a restaurant owner, chef, who makes food based off of what she could buy locally that day. So she didn't know what she's going to cook that day. People who come to the restaurant have no idea. The menu is literally printed out every single day. So they wake up really early and they drive to this was in California in the Bay Area. So they would drive to Fisherman's Wharf to see what fish came in. Then they would go to local farmers markets, of which there are lots, because most of the fruits and vegetables in the United States are grown in California. So they had a lot of opportunity to get stuff. And so she would just buy the best looking things. And then her and the other people who went out buying, they would get back and they were like, all right, this is what we got. Let's make something. And so she deemed that as organic food, meaning that it was locally grown, sourced, and there was also like the type of farmers that they were, more small farmer. And then the federal government got involved with this and decided to classify organic food as something very specific. So you could name, your mac and cheese is organic. And now it has to do with which pesticides are used, how much pesticides are used, and how the farming techniques are accomplished. It's really got less meaning than it used to. And again, Alice's method is the best, to just find people who grow food and go buy directly from them. But organic has a completely different meaning when it comes to chemistry. And this is what it means. So what we're looking at here is a table of carbon with the different substances attached to it and the oxidation numbers of those substances. So in the one on the far left, the carbon's charge is -4. The hydrogens are all +1. So if you've got an atom and its oxidation state is -4, tell me something about it. Why does it have a -4 oxidation state? How does something get a minus charge in the first place? That's not a possibility. I know we just left nuclear, but we're back into chemistry again. So can't lose protons, gaining electrons. So tell me about this carbon. What did this carbon do? Why is this charge +4? Sorry, -4. Gain 4 electrons. We okay with that? Effectively, it has 4 electrons, extra electrons. How many electrons does a carbon have? 6. So how many electrons does this carbon have? It's controlling 10 total electrons. And it can't control any more than that, because that gets us to neon. And so it's not going to go past neon. Remember, it's either going to gain 4 electrons or lose 4 electrons. Gaining 4 gets it to neon, losing 4 gets it to helium. And so you can't lose those last 2 electrons. So your options are anywhere between -4 and +4. So what happens when I move over one spot? This is methanoic acid. That first one was methane. What's the oxidation state on the carbon this time? -2. So tell me what happened to it. Related to the first one, first option. This guy's got 4 extra electrons. How many extra electrons does this one have? 2. So what happened to those 2 electrons?
sharing the oxygens too?
The oxygen took it.
Okay.
Oxygen's electronegativity is huge by comparison. So it took it. So what's happened here? What's the oxidation state on the carbon? Tell me about the extra electrons that this carbon has. Doesn't have any extras, right? Its oxidation state is 0, so it's got 4 valence electrons. So it's what happened to those 2 electrons that it had over here? So this is 1 bond to oxygen. 1 bond to oxygen took 2 of those electrons. This is still just 1 oxygen, but now it's 2 bonds to 1 oxygen. So that oxygen took 4 electrons. How many bonds to oxygen are there here? How many bonds to oxygen? 3 bonds to oxygen. So now it's lost 2, 4, 6 electrons. So now its charge is +2. How does an atom have a +2 oxidation state? Has 2 less electrons than it does in its atom. So I have regular old carbon with six electrons. This guy lost 2 of those 6 electrons. Now it's only got 4, so its charge is +2. How many bonds to oxygen do I have here? 4. And its charge is now +4. So it lost the last 2 electrons that it can lose. So a carbon atom has 6 electrons. It cannot lose 2 of them. The last 2 are completely and utterly off limits. But the first 4 are available to be lost. But it can also gain 4 electrons. So in this methane, it has gained those 4 electrons. And when I go all the way down to carbon dioxide, how many electrons total has it lost? If it started at methane, I burn methane and one of the products is carbon dioxide. How many electrons did that carbon lose along the way total?
What was the question?
How many electrons did methane's carbon lose to get to carbon dioxide? So methane, the carbon has 4 extra electrons. And when I go all the way down to carbon dioxide, it lost those 4 extra electrons, and it lost the 4 that it can lose. So this process, it loses 4 electrons. Those electrons do stuff. So in the easiest example, this is methane gas. This is very flammable. If you drive down to the sewage treatment plant in Hood River at the port, or down here in the Dalles, there is a pipe that's got a flame coming out of it. You notice that? Like right now, every sewage treatment plant in the country, unless there's a problem, has a flame coming out of it. Why? Because poop generates methane. And a sewage treatment plant concentrates poop. And so a lot of methane gas is produced. So you have 2 options. You can either, I guess you have 3 options. You could capture it. Most places aren't ready for that. You could burn it, which is what most places do, or you could release it to the environment, which is terrible because even though carbon dioxide is a greenhouse gas, methane is a greenhouse gas times 20. So it's 20 times worse to release the methane than it is to release just the CO2. So they'll just burn it on the way out. Plus, if it's like a no wind day, like in the Dalles, you can have a temperature inversion where there literally is no wind. And you know what those days are like. Smoke coming out of a wood stove looks like this. It hits a temperature inversion and stays. So now everybody in the Dalles, because of the fact that it's got hills all around it, and if there isn't any wind blowing through here, all of this stays in here. And so the emphysema numbers at the hospital, like go through the roof 24 hours after this starts. So people who have lung problems, they'll be in the hospital, in the ER on oxygen. Or they'll be at home with oxygen levels increased because they can't breathe because their lungs become more inflamed than they normally are because there's more particulate in the air. So if you see this kind of situation, if the sewage treatment plant's methane burner wasn't working, then methane would build up right there at the plant and it would actually be super dangerous because it is a significant amount of methane. I mean, the pipe is like this big and there's a flame just constantly shooting out of it. So what is going on with those 8 electrons? They're being used to generate heat and light. That's what's going on when I burn it. But we don't have to burn it. You can turn it into different useful products. Each of these is a useful product in its own way. That last one, this is useful. So what is the difference between organic chemistry and inorganic chemistry? Is carbon. And more specifically, it's the number of electrons that the carbon is. Or more importantly, does the carbon have any electrons that it can get rid of? This carbon is the most organic carbon there is. It could potentially lose 8 electrons. And each time we move over and it's lost 2 electrons, it's a little less organic. These first 4 options are all organic versions of carbon because they could give electrons away. The CO2 at the end is inorganic carbon. So what's inorganic carbon mean? It's carbon that doesn't have any electrons to offer to a chemical reaction. It could accept them, and you need something like photosynthesis to make that happen, or electrolysis to make that happen. But if I'm carbon and I only have 2 electrons left, I am now considered inorganic carbon. So the 2 most common places to find inorganic carbon would be in carbon dioxide and in carbonate. So like baking soda, there's a hydrogen carbonate there. The carbon inside of that is got multiple bonds to the oxygens, and so 4 bonds. And so it has no electrons it can give away. So for our purposes, organic chemistry means carbon has the ability to give electrons away during a chemical reaction. So these first 4 are organic carbons, and the last one is inorganic carbon. Let's talk a little bit about the history of this. There is something that was around for maybe 200 years called vital force theory. Okay, so this was a churchy kind of thing. Let's use this one. Maybe this one. That's not what I want. This is a graphical representation of hemoglobin. So these little blue things here, these are hemes. The green thing in the middle is the iron, and these are globins. These are proteins. This is a massively, as far as molecules go, and as far as this class goes, a ridiculously big structure. This is another one, same kind of situation. I've got all of these different atoms, all of these different proteins connected together to make these globin proteins with these heme molecules stuck inside of them. Do you think that we would like to be able to make this in a lab? Give me reasons why we would like to be able to make hemoglobin in a lab.
blood, please. You could make blood.
That's blood, right?
Right.
What, why would I want to be able to make blood? Obviously, so the vampires would leave us alone, but what are the other reasons? You could make any type, right? You should be able to make any of those types of blood, right? So we wouldn't need to have like blood drives. So the blood would be safe, right? You wouldn't be fearful that the blood would have a hepatitis in it. Maybe an unknown type of hepatitis. Maybe hepatitis E is out there and we don't know it yet. And people are given blood unknowingly, they have hepatitis E. And now that hepatitis E is going to be given to people. I mean, I don't know if you know this, but gay men specifically in many states and countries are not able to give blood because there was the HIV fear. So the other awesome thing about this is if we were able to do this would be, let's say we have a surgery. It's a long one, like someone's got a weird open heart surgery, there's some sort of cancer, and there's a lot of blood loss. Well, if I basically got an unlimited supply because I can synthetically make it, then your entire mindset will change. Like we've only got X number of pints of blood to make this happen. So we have, a time constraint and a volume constraint. And if I had like gallons of it, then you could do lots of different things. You could literally just like pump gallons of blood through the person's body with like veins and arteries open, just dumping the blood on the floor because nobody cares because I've got plenty of it. As long as it's oxygenated blood and it's going through the system, it doesn't care if it makes it back anywhere. If it just ends up in the floor and somebody cleans it up later, that's fine too. As long as that person is oxygenated during the process. Wars, gunshot wounds, ERs, like people would love to have this. I don't know where the broken arteries are from these 3 gunshot wounds. I'm just going to keep feeding gallons and gallons worth of synthetic blood into a person until I find the problematic veins and arteries. Car accidents, same situation, right? You could just pump the EMS guys could show up with this giant tank on the back, or I don't know, they'd probably need several giant tanks depending on what blood type you are. Or no, they would just make O, right? Huge tank O, and that's all you need, right? And then 1 tank AB, right? 1 tank AB negative or AB positive, and then you take care of everybody. So, but we can't do it. Why can't we do it? Because that's complicated. That molecule is super complicated to build from scratch. We've built lots of molecules. We've built insulin from scratch. We don't do it that way anymore, but we can build it synthetically in a lab without using an organism, although using a virus is a better way to do it, and that's what we're doing now. So the issue was because these organic molecules were so complicated to chemists hundreds of years ago, they came up with an idea that it's too hard. And the reason it's too hard is there's a vital force that all living organisms have. And because they have this vital force, and what they were saying is because things have a soul, that soul is what allows the body to build proteins that are structurally complex. So what they're saying is there's some kind of magic that happens inside of a living organism, and that magic allows super complicated things to be created. Does anybody know the flaw in that logic? Because the church is the people who came up with this. Does anybody know how they're like condemning themselves? Yeah, what about trees and plants? Well, they just said that the trees and plants have a soul, right? They burned a guy 1800 years before this for saying that same exact thing, Epicurus. So does everything have a soul, or does nothing have a soul? Because that's what you're saying. That's what's going on here. So this guy named Wohler, he's finishing up his postdoc in Switzerland. I think he's in Sweden. He's finishing up his postdoc in Sweden, and what he's
what he's been doing is collecting urea from human urine and animal urine and studying urine for his person, the person he's working with. Whatever, fine. He leaves his postdoc. He goes to France. He's trying to break this. He's trying to break the vital force theory. And he and another guy react ammonium cyanate, and they create urea. Well, urea is a complicated protein that we know comes from living organisms, whether it's a dog or a person. So he just proved it. That thing right there, we just made that thing. So vital force must not be a thing because that's an organic molecule. And his partner was like, "Are you sure that's urea?" And he's like, "Come on, you know who I work with. I've been working with P for 4 years. I know exactly what urea crystals look like." And he was right. I mean, they were urea crystals. You can do several chemical reactions to determine it, but the easiest thing that most people do is just do a melting point test. And the melting point test will almost, I mean, we're talking about like melting point test to a decimal place. And so you're pretty sure that that organic molecule is what it is. That's the quickest and easiest way to determine, like, is this methamphetamines? Do a melting point test on it. If it melts at exactly this temperature, then there's almost no chance that it's something else. All right, so he goes on a whirlwind tour, literally across the entire world, telling everybody, "Hey, I'm going to do this experiment in front of you, and when I'm done, you tell me what I just made." And they're like, "Oh, you made urea. Oh, wait, vital force theory is not a thing." So it took a long time for people to be, they literally were like, "Oh, we can't make organic molecules because of vital force." So they just didn't do it. And then Wohler was like, "Yes, you can. Here, I did it. Now what are you going to do?" So now everybody was like, "All right, so that's dumb. Let's start making these molecules." And we started making these molecules. There's an entire sect of chemistry called natural product synthesis. It's an incredibly important sect of chemistry where we know something in nature does something, but I don't want to have to kill every single puffer fish on the planet to get the stuff that I want. So I'd like to just pull it out of one puffer fish, look at it, and then have somebody build it in a lab. That can be super problematic for this reason. Maybe it's not as complicated as the hemoglobin molecule, but I still need to build that thing. And so let me pull up another one of these. We'll just go like this. There's the heme molecule. That's that thing. There's each of the hemoglobins have 4 of these, 1 per globin. And so that molecule right there is fairly complicated. We've talked about before that any of those turns and corners that aren't labeled have carbons on them. So all of these things are carbons. These are double bonds between those carbons. And so you can imagine that if you start off with raw materials and you need to build this, there can be problems when you're building. So, you know, maybe I build this acid here and I build this ring structure and I start to build this ring structure. And then when I try to add this nitrogen here, this acid here falls off. So then you have to figure out a new pathway. Maybe you don't start with that acid. Maybe I start with the ring structures. And so what a person who is under natural product synthesis does is they take a molecule that they know is biologically benefit, like the molecules that you guys are writing your papers on, and they try to make it in a lab. And maybe they get halfway through it and then they graduate and then somebody comes in and takes over their product, the process that they have done. And so that's a pretty common thing. And so then once it actually becomes synthetically viable, then they'll give it to a chemical engineer, and they'll figure out a way to upscale it to make lots of it. So there are lots of molecules out there that we make that you could get from plants or animals, but we just don't want to have to get them from plants or animals. What's something that we really would like to be able to make because we're going to run out of it in maybe 100 years? Petroleum products. What happens when we run out of petroleum products? What do we use petroleum products for besides just fuel? These buttons are made out of crude oil, right? This bottle was made out of crude oil. That tabletop, that Formica tabletop,
crude oil. The carpet, crude oil. The board, crude oil. Blinds, crude oil. There's a lot of crude oil around you. So what happens when we run out of crude oil? How are we going to start making blinds and CO2 bottles and Formica? Well, we can make them. It's just a lot more expensive than it is to just pump stuff out of the ground and refine products and then build from there. But when you buy synthetic motor oil, what are you buying? Somebody started with methane and made oil out of it. Not super hard for us anymore. It wasn't dramatic. It was like 10 times more expensive when it first came out, but now it's not 10 times more expensive. It's maybe twice as expensive, maybe less than twice as expensive. But why would you want to buy synthetic motor oil as opposed to motor oil that came out of the ground? Has anybody changed their oil? If you change your oil, that's regular old oil, the oil is black, like black. Even if you have the ability to change the filter without taking the oil out and start the car, the oil will still be kind of black. The synthetic motor oil, you run it, then you have a way to take the filter off without draining the oil out. You put a new filter in, you start the car, the oil looks brand new. That's because the oil that comes out of the ground came out of the ground. So no matter how much you purify it, there's still stuff in it you don't want. The stuff in the lab, you made it. So you know exactly what it is. So it's exactly the products that you want. And so, you get a purification without having to purify anything because you started from scratch. So Wohler is like, started everywhere along the path to, we can start making stuff. So let's start making stuff. And it is definitely, like, if you think about chemistry, natural product synthesis is one of the most chemistry things you can do. There's Wohler. And I'm going to talk about carbon like Legos all the time, because what do Legos like to do? They like to connect to each other, but then what else can they do? We can disconnect from each other without being harmed and then connect to each other in a different way. So the best part about Legos is you can build pretty much whatever you want. I'm not a huge fan of all the new Lego kits that you buy that have like specialized pieces. I'd rather just have the blocks and it looks Minecraft-y, but regardless, you can build what you want out of it. And so the same situation with carbon. How many organic molecules are there? I don't know. It's probably close to infinite because you can do whatever you want with it. It's like saying, how many possible Lego structures could you build? Number's too big to think about. So, and that happens because carbons like to connect to each other and they're fine disconnecting and reconnecting to themselves in different ways. So this is straight octane. This is not including a carbon, but this is the thing you start with, octane. And this is the precursor. You really know what this is? The base skeletal structure for? Cholesterol and all steroids. But your brain is like 90% cholesterol. So add some stuff on this on the sides and you got yourself cholesterol, and you need to make testosterone, estrogen, progesterone, and all these different steroids that signaling things and also building structures. The myelin that surrounds all of your nerve endings, all of your nerves all the way through, cholesterol. So super important molecule. And again, what I've connected in interesting ways and can connect it in lots of interesting ways. All right, so we did talk about hybridization. So we're going to do that again. So we know that this is the second energy level for the carbon molecule for hydrogen. So it's instead of having an S sublevel and 3 S orbital and 3 p orbitals, they come together and give you 4 orbitals at the same energy level with 1 electron in each. So this is what normal elemental carbon looks like. Meaning you lose those 4 electrons and turn into inorganic carbon. So if those 4 electrons are gone, that would be carbon and CO2 or carbonate. Or I can add 4 more electrons here and that would be methane, and that would be the most organic carbon possible. I can make a double bond by moving one of these up to its own p orbital. I have 3 different connections, and then a second connection to those 3 different things. And then I can have sp hybridized, where there's connections to 2 different things, and then 2 more double bonds, either 2 to one side or 1 to each side. But for, again, every single time we do this, we've got 4 bonds. Where are these organic molecules, or what are their properties? They are going to be flammable. They're, for the most part, going to have a high vapor pressure. So they'll turn into a gas fairly easily. Many of them have an odor, but not all of them. Do you guys know what the highest rated smell is by humans? Good, sorry. Say again? Gasoline's number 1. It's that, I can't remember what do they call it. What do they call it when you've got several choices and you put 1 next to the one you really want, and a 2 next to the one you kind of want, and a 3 next to the one you don't want? It's a type of voting that we should probably be doing. Anyway, you understand. Nobody puts gasoline as number 1, but everybody puts it like 2 or 3. So maybe cinnamon's number 1 for you, but it's not number 1 for most people. So what ends up happening is the gasoline gets bumped to the top. They're covalently bonded. They're non-polar substances, so they don't mix with water or any other polar substances. Phenomenally low solubility. I mean, you can get some of them in the mix under certain circumstances. Normally found as gases or liquids at room temp, but could be solid, and they're non-conductive electrically. So no current's going to run through them no matter what. Well, not no matter what, but typically. Okay, so we need to talk about formula types and how these organic molecules are going to be shown. The first one we know, that's a chemical formula. We've seen the structural formula before lots of times in stuff I've drawn. You've seen the condensed structural formula underneath that, where we take the structural formula and put it into a way that I can type it. So that's a carbon with 3 hydrogens. Carbon with 3 hydrogens. Carbon with 2 hydrogens. Carbon with 2 hydrogens. Carbon with 2 H's. Carbon with 3. Carbon with 3 H's. So you can go back and forth between those. And then the last one that is specific to organic chemistry is the line structure. So all of those things are trying to show the same thing. Carbon, 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 carbon. What's not being shown in the line structure? They make the assumption that you know how many hydrogens are supposed to be there. So since all the carbons need 4 bonds, and this carbon is definitely connected to that carbon, but only 1 carbon. So this carbon here must need 3 H's. Since this carbon is connected to that carbon and that carbon can only have 2 H's. So that's how we get the structures out of those. So the line structure is just chemists being lazy. Honestly, because drawing the structural formula is just a pain in the butt. All of those line. Okay, let's talk about sources of organics. Crude oil. Most of them come from crude oil. We can get some of these things from plants and some of them from animals. Between the 18 and 1900s, around that time frame, what was the largest source of organic fuel on the planet? Whale oil. Yeah. I saw something pretty awesome. Did you guys see Star Trek 4? It's a 90s movie. No. 1 is weird. 2 is fantastic. 3 is okay. 4 is great. So even numbered ones. The premise of the movie is something is coming to Earth and it's basically destroying everything in its path.
they realized that, and it keeps sending like this weird harmonic sound at Earth. Turns out it's the sound of humpback whales. That's what they determine in the movie. So we've killed all the humpback whales. So they need to go get some humpback whales. So they literally do a slingshot around the sun, go back in time to like the 90s, get some humpback whales, come back to the future, put the humpback whales into the ocean, and then the humpback whales talk to whatever is coming from space to destroy Earth, and it goes away. So it's actually pretty funny, and it's quite well done as far as the sci-fi movies go. But the best part about it, and the reason I mention it, is because of that movie. Since that movie came out, the humpback whale population has skyrocketed because that movie got governments to stop whaling humpback whales. It's got some outliers still. Japanese there's still people pirating that come from Japan and other Asian cultures, but for the most part, the whales have rebounded. There's a great scene in the movie where they're about ready to kill this whale, and the ship that they brought from outer space is literally in between the whaling boat and the whale, and it's invisible. And they shoot their harpoon, and it just like bing off the hull, and then they make themselves visible and like go away. Like, we're protecting these whales. So we don't need whales as the impetus, but you almost certainly had a whale oil lamp in your house, one of them, sometime in the late 1800s, early 1900s, because that was the source of hydrocarbons. Obviously, we don't use the whales for that anymore, and we get it out of the ground. Well, I'll give you a little more description of that a little bit later, but I want to talk about this term cracking. So gasoline, I'll just draw it. So a little earlier up there, I had an octane molecule. So 2, 3, 4, 5, 6, 7, 8. So I'll stop for a second and say, this is the best way to draw line structures. You put your pen on the paper and then say 2. All right. Because you put your pen down and say 1, 2, 3, 4, 5, 6, 7, 8. Otherwise, you're always going to draw like one too many. Like if you start here and go 1, you've already drawn 2. So don't do that. So that's an octane molecule. This is not what you buy at the gas station. You actually buy, this molecule. So it still has the formula C8H18, but the molecule structure is a little bit different, obviously. What we've done is we've pulled off these carbons and attached them to different places. This is what cracking is. And so this is important because it allows your vehicle to run correctly. So I'm gonna put something up here. The one I want. Go. Okay. This is how your car works. Most cars have 4 cylinders in. So I've got a camshaft. I've got 4 different pistons. I've got piston rings. I've got 2 different types of valves. There's an intake, which is blue, and then there's an exhaust valve, which is red.
So let's just take one of these guys. So the piston is going up and down. And then there's the bluish color is when gas and air is being let into the piston. And the orange is when the explosion happens. So I basically got different things happening here.
You know, I can't stop this, can you? Yeah, that's what I'm doing. That's good.
Right, so we've got everything all on sync. Okay, so this piston is headed down. When the piston is headed down, the intake valve opens. It lets in air and fuel. When it gets to the bottom, it starts to come back up. And when it comes back up, you'll end up having this stuff. That's what this one's doing. So this valve is open as the air and fuel come in. You close both valves. And when the piston gets all the way up to the top, then the spark plug sparks and it throws the piston down. That's the entire point of the internal combustion motor. There's an explosion that makes an up and down motion turn into a rotational motion with a camshaft. The camshaft is just a rod that's got offset sections to it. Here's the offset section. This thing inside the piston can turn back and forth, and this is rotating around a central camshaft. So this explodes and pushes down. But now once this has happened, I've got a container that's filled with exhaust fumes. And so I need to get rid of the exhaust fumes. So then it comes back up, and when it comes back up, it opens up the exhaust valve, and then all of your exhaust comes out. And then once this reaches the top, then this valve closes, and I get this process occur. So what is something bad that could happen during this process?
There are multiple answers here.
Sure.
So one thing.
I'm looking for one specific, but there are definitely multiple answers here. Some obvious things are, what if one of the valves doesn't close? Or one of the valves doesn't open? So let's say the exhaust valve doesn't open. Well, then that piston isn't going to do anything, right? Because it's filled with exhaust, so it's not going to burn because it's filled with exhaust. Plus, it can only pack so much gas inside of it. If one of them's open, let's say during this explosion process, the exhaust valve doesn't completely seat. Then as this is going up, the fuel and oxygen are coming out. Have you ever seen that? Me? Any of you? Yeah. I'm sure all of you have seen it. What does it look like? No, I'm not talking about the explosion of the engine. It's that car in front of you whose exhaust is blue and stinks. That means one of these exhaust valves won't completely seat. And so when this comes back up to get to the top so it can explode and go down, some of this good stuff is seeping out. So that car is not efficient because it's literally just pumping gasoline out the tailpipe. That's not burning. So any blue exhaust is a bad exhaust. So those are terrible things. The spark plug, maybe it doesn't spark. Obviously, that's a serious problem. That's usually the problem that people are experiencing right now when they're trying to start their lawnmower for the first time this year. Just go start like every single small engine mechanic will go. Just start with changing your spark plug. The biggest issue would be, what if when this opened and fuel and oxygen came in, instead of it waiting for it to be working its way back up to the top, that it exploded before it got to the top? What if this piston is working its way up to get to the top, and before it gets up there, it explodes? Well, that piston has one option. It can go up right now. So if something pushes it down, it's pushing against a cam that is moving in this direction. So if we were to try to go down this way, it would try to be, it's pushing against the rotational energy of the camshaft. So terrible to break this rod thing. But it usually happens, if it does happen, it usually happens near the top. And you may have experienced that, you probably have heard it before, but it's knocking and pinging. So the car is running and it sounds like, I don't know, there's ball bearings running around inside of it. It could be kind of faint or it can be kind of loud. And that happens when the fuel ignites too early. And that happens, one of the reasons that can happen is if it's got bad fuel. So if you buy a high-end car, if you buy like a WRX, the little gas cap thing says you need to put at least octane 89 in this. You can't put 87. We want you to put 92 in, but you need to at least put 89. I think all BMWs have the same requirement for them. And the reason is those vehicles run hotter than normal vehicles. And the reason that they run hotter than normal vehicles is because they want the car to go fast. The amount of energy that the car can produce is a differentiation between the exhaust temperature and the explosion temperature. So if it burns hotter, it can generate more power. So if this car runs at 50 degrees Fahrenheit hotter than the next car, then the chances of this prematurely exploding is a definite possibility. Then you damage your BMW motor, WRX. It would be very obvious to a mechanic that that's what happened and you void your warranty. So why? Because when you buy the differences between buying those types of gasoline are how much of this regular octane is still in the gasoline mix. And the weirdness is this one here that's a straight chain will actually ignite at a much lower temperature than this guy here that's got a branched chain. So the reason you want to buy a higher octane fuel is to make sure that you have less of this, and so there's less of a chance of that knocking and pinging occurring, because you shouldn't be using that. Yeah, right there. So where does all this stuff come from? This over here on the left is called a fractional distillation tower, or a fracking tower. Fractionation tower. So the fractional distillation that you guys did, where you had the mixture of ethanol and water, and you separated it out, that 121 experiment, we did that first, maybe third week. That's really what that thing is, this thing here. This is a much more complicated version of it. So you dump in a bunch of crude oil. The crude oil is heated up to a fairly high temperature, like 370 degrees Celsius. There can be no oxygen present, otherwise this flammable substance will catch on fire. So it's, 370, that's what's that, over 900 degrees Fahrenheit. It's on. So it goes in and it's all a gas. And literally, when I'm saying a gas in this circumstance, I mean the phase of matter gas. So it comes out and it immediately starts to cool down. And what it's going to do is it's going to start making its way up this fractional distillation tower. The further it gets away from the source, the cooler it gets. The stuff that's the longest chain will not even make it through the first barrier and will end up liquefying and just dump to the bottom. So do you recognize any of those names down there? Can you read that? Okay. That better? So paraffin, which is that stuff that we have next door that's sort of like saran wrap meets wax paper, wax is asphalt, coke, which is
So. Yeah. That's exactly what Coke is in happens. And, I'm not sure if we realize that, but that's what asphalt is. The dregs of the oil, crude oil. Like carbon chains of more than 20 carbons in a row. So we keep doing that up, down thing, where there's more than 20 carbons in the chain. And because the carbon chains are so long, it's like having a really long piece of Velcro versus a really short piece of Velcro. So a short piece of Velcro you can pull apart pretty much at any angle, even like tearing it across itself. But a really long piece of Velcro, you're not going to get that off. It'll slowly pull apart. With these things attached to each other, Coke's a solid, asphalt's kind of a solid, right? How come I'm saying it's kind of a solid? It gets poured out, right? It comes out of the back of an asphalt. I mean, they do a good job of like forming it. It's like a Play-Doh-y kind of situation, but at a really high temperature. And then if you've been around when new asphalt's been laid, it smells like oil. Why? Because it's oil. There's going to be some remnant, smaller, shorter chains within those 20 plus carbon chain things that smell like regular old crude oil because it's going to be embedded. So we were just talking a little bit about what happens when we run out of crude oil. And I was talking about not having blinds and countertops and bottles, but what else are we also not going to have? Roads, fires. We're not going to have asphalt roads. Is that important? Why can't we just make them out of concrete? Like 100 times more expensive than asphalt. So are there sections of the roadway that are made out of concrete? Bridges for sure. Anything else? The bridges might still be surfaced with asphalt. The asphalt's smooth. It can be replaced fairly easily. They're doing that in Dallas, or sorry, in Hood River right now. I saw that they just put down the asphalt for Cascade, so we wanted to do the detour and soon. Do you know the song Route 66? Been redone a few times. No. They made songs about it because it was the first road that went from one coast to the next coast. If you drove on it now, you'd be like, this is a back road. Now you get on like 80 and just or 84 and run across. All the even numbered interstates are east and west, and the odd ones are north and south. And so when Truman decided to jumpstart our economy, and if you buy something, how did it get to the store that you bought it? A truck. So how do you get trucks around? Well, you don't have them drive on roads like Route 66. You have them drive on roads like I-84. So Highway 30, they're reopening for a bike path and walking path. That was the road. Did you imagine trying to get to Portland on that road? I mean, it's a 3-hour drive, right? Because lots of places you're driving like 10 miles an hour. I mean, think about the twin tunnels. Like that was the road. The whole road was the twin tunnels. So very narrow, can't go very fast on it. So Truman decided that the federal government would spend an obscene amount of money and build a ridiculous amount of very high quality, high speed interstate highways. And he put that out in his government. People came in and were like, yeah, we would like this. And they talked about where the road should go. And every town that got one through it, its economy skyrocketed. So all the towns were like trying to get their town to be the town. Like Bend was fighting to have I-84 go through it instead of coming up here. But obviously the river won out. It's more important to have the river right next to the road than having run through the central part of the state. But when the Pentagon looked at it, they said, this is great. We'll be able to, if somebody were ever to invade the United States, Red Dawn kind of style, Red Dawn movie. We only talk about the one from the 80s. The Pentagon said, all right, so we have a requirement. We want these sections of the road paved in concrete. And I know it's more expensive. We'll help foot the bill. Does everybody know why they did that?
Because the width of a lane is the width of, I can't remember what it's named, the tanks are.
Might be wrong. No, that's not it. I mean, the width might be the reason that the whole road is as wide as it is. But there's another reason. But they needed to be made out of concrete.
The tracks will width through asphalt, not through concrete.
No, tracks will break concrete. No, it would probably indent. I mean, the asphalt won't break unless it's really cold outside. It'll just sort of Play-Doh. So this was asphalt, right? It's a hydrocarbon. What's the first property of hydrocarbon? It's flammable. Okay, so is that a problem? In the 50s, what aircraft do we now have? That we didn't have during World War II. Yeah, we have jets. The jet wash will catch asphalt on fire. Jets do not land on asphalt. They land on some kind of hybrid structure or they land on concrete. Why? Because the jet wash could ignite the asphalt. What happens if the asphalt gets lit on fire? It's a Class D fire. So a Class D fire is you don't put it out. You just let it burn itself out. This happened in Philadelphia the last year that I lived in Pennsylvania. A tire factory that had part of its yard underneath an overpass on I-95, which is probably the most driven freeway in the country. Goes from Maine to Miami. The tires caught on fire. Tires burned very hot. It heated up the bridge overpass and caught the asphalt on fire. So what did they do to put it out? Nothing. They used bulldozers and just cut the asphalt, like literally dug a trench. So it just burned itself out to the two trenches. And then they spent like a obscene amount of time rebuilding it. Traffic was, you just didn't even bother. Like we had tickets to go to baseball games. We just, not even bother. As soon as that, I mean, can you imagine all the people that lived around that? Their quiet little neighborhoods turned into freeways. The most fast freeway in the United States. So the Pentagon said, some of these sections can't be made out of asphalt. So when you're driving into Portland next time, getting close, like Troutdale-ish area, observe the road change and then observe the fact that there are no power lines there. The power lines aren't allowed to go anywhere where the concrete is because that's where the planes can land. So if somebody invades us, we have the ability to land our planes in strategic areas, which is outside of every major city. Even every city's got a freeway.
Okay. So if we go up a little bit, the first true vapor stuff ends up turning into lubricating oil stock. So these are carbon change from 16 to 20. And do we know what kind of lubricants we're talking about here? Anybody pack the wheel bearing? This is the kind of lubricant grease you do not want on you. I've definitely had it on me a couple of times. We were talking about washing your hands like 10 times with 10 different types of soap and trying to get it to go away. Seriously considering just putting my hands in straight bleach. Like that's how bad it is. And the reason that these things are used because they can withstand high temperatures without breaking down. So all of your cars have bearings around the wheels and axles, and inside those bearings, there's a lubricant. And that lubricant needs to stay in there because it's allowing a reduced amount of friction. If the lubricant goes away, the bearings will end up producing a whole bunch of heat, and then your tire will either seize or catch on fire. So you need that lubricant to stay in. And so you need a lubricant that can be at a pretty high temperature because your car's going to be driving pretty fast, producing a significant amount of rotational motion and friction. And so I need it to not get so hot because if it gets too hot, then the lubricant actually turns into a liquid and it just seeps out the seal. And then everything locks up. So I need something very thick, basically, to
to make sure that it doesn't liquefy. When I move up a little bit further, I'm at 15 to 18 carbons long, and here we get heating oil and diesel fuels for industry use. Like, these are the diesels that like a train would use, or like a ship would use, not like residential commercial pickup truck like the other one we got. Also, some of you might have heating oil houses. I don't know if they're still around. So you spend about $100 and somebody comes in and just fills up a tank with oil, and then that's what your furnace runs on, that oil. We also start using these materials for cracking. So you can break these 50 to 18 carbon things down into smaller chains or rearrange them to make them into
Less susceptible molecules, molecules that can withstand higher temperatures and conditions. If I move up a little bit further, I get some kerosene, so 12 to 16 carbons. We might have used a kerosene lamp before, but usually just use this for we just use for heating, but we use it for lighting. And then regular tractor and regular motors, diesel. So also more cracking stuff. And as we get further and further away, the carbon chains become shorter and shorter. And that's because the shorter and shorter chains can be a gas at a lower temperature. So nothing that's going to be, say, 18 is going to make it this high, because it would have liquefied here because it's got greater intermolecular forces because it's longer. We go up a little bit more, and we've got the two most talked about and probably most important to us. Carbon change between 5 and 12. What important number falls between 5 and 12 as far as we're concerned? 8 octane. So when they built the first internal combustion motor, it was the diesel. It ran on peanut oil. We decided we couldn't create enough peanut oil to power what we assumed was going to happen with the internal combustion motor. So they redesigned it to run off of hydrocarbons after we realized that hydrocarbons were a thing. The first real well was found on a farm in this was Mark Forest in Pennsylvania. And so when we found that and we started looking around at what we could do with it, we decided that we were gonna, since cars were gonna become a thing, engines were gonna become a thing, that we would pick the substance that came off the most out of crude oil. So of all the substances, carbon chain lengths 1 to 50, 8 was the largest percentage. I mean, it's still a small percentage. It's still like 12% of all of them. It's 8, but it's the highest of all available. So they decided to design a motor around being able to burn octane. They didn't bother cracking it at first, because those cars and motors weren't hot enough to make that an issue. But we went with 8. And so that's why cars now have spark plugs instead of not having spark plugs, because you need one for a regular gasoline vehicle as opposed to a diesel motor. And so, yeah, that's why we use octane. And then the last one here, we've got 124. So that's methane, ethane, propane, butane. And obviously we use the methane, ethane, and propane for anybody who's got natural gas or anybody who is using either that for like heating their water heater or their furnace or their barbecue grill. And the butane is one of those 4 things that's actually a liquid when you get to room temperature, although it's really close as far as it being a liquid or not. So this is the traditional method that we use to get all of these substances, especially these top 2 boxes. But we're using another method to get these natural gases, the methane, ethane, and propane in the US. Do you know what we're doing now? Get all that stuff? The US is actually an exporter of oil. We don't buy oil. We don't need to buy any oil from any foreign countries. We make enough of all of this stuff ourselves now. How do we all of a sudden get that way? Yeah. How do we increase our production of natural gas?
We're not pulling more out, are we?
We are pulling more out, but we figured out a way to pull it out. That always makes it a good battle start a lot. fracking. We've heard that term before. So what fracking is you have a lot of natural gas locked away in rocks. So what we do is we drill a hole and we squirt a slurry of terrible things into the hole, and that hole cracks open these rocks and natural gas comes out. A lot of natural gas, like so much so that we have built specialized tankers to move natural gas around the world to sell to other countries. They're really funny looking. They just basically look like a giant propane tank because they're basically a giant propane, as opposed to the oil ones, which just look like regular ships. The bad part about the fracking is two things. One, they're terrible at actually collecting the natural gas. A boatload of it seeps out. So that's a lot of methane, ethane, and propane that are released into the atmosphere, which are much higher concentrations of global warming gases than just CO2. And the other thing is that terrible slurry of garbage that they send down to crack open the rocks ends up in aquifers. And you might have seen these weird YouTube videos where somebody will turn on their sink and then put a match next to it and then their sink catches on fire. So that's these fracking byproducts that have broken themselves into an aquifer and now leaking into the water. So the water itself is basically like propane grill level of gasoline of natural gas, and these other the fracking slurry, and it makes the water undrinkable. It just tastes like you're drinking what gasoline smells like.
But at least we're exporting instead of importing now. I'm being facetious with that. So,
Because of what Wohler did, we realized that all of these things that we get out of the ground, we can just make that. We will do a lot more of that in the
future, because we won't have stuff. We won't have the stuff coming out of the ground, so we can just convert stuff into. Does anybody have any idea what our source is most likely going to be of hydrocarbons? Could be algae. We can actually have algae grow crude oil, gasoline, diesel, engine oil. What'd you say, Grayson? Most likely it's going to be corn. We'll use corn. We'll break the sugars down, and it'll probably almost certainly be the cob part, because we'll eat the corn part. They'll use an extraction process to get it's easier to pull the glucose molecules out of the corn cellulose than it is out of wood cellulose, because there's less of the ligand protein in there. And then we turn that into ethanol. And then from ethanol, we can make whatever we want out of it. So almost certainly the synthetic motor oil that you purchase will be a product of some guy's corn in Iowa. The ultimate source of it. Yeah, I'll call it good for now, although we'll talk about.
briefly talk about this. We'll just leave these kits in here. But, make sure you guys all have the same ones. So for these kits, these white ones are going to be the hydrogen. These black ones are going to be the carbons. The hydrogens only have one hole bored, and then you can only make one bond. The carbons have 4 holes bored in a tetrahedral shape. They can make 4 bonds. The little ones are sulfur, they've got 6 holes in them. The greens are chlorine, 1 hole. Iodine, purple, 1 hole. And then these should be nitrogens. These blue ones are nitrogens, they have 3 holes in them. Great. Phosphorus. You have 5 holes in them. Then the oxygens have 2 holes in them. And then I'll give it next 2 bonds, and then the orange is bromine. We've got both. The have, some longer ones to connect that. Have a lot of shorter ones. These are the ones you usually use with the hydrants. And then you got springs, and the springs are used to make double and triple bonds. So, like combine the springs over and make sure they're connected. To the storehouse.
I think the whole bond, do they always like top bottom,
Yeah.
in 3D? Stay black.
So this is an incredibly important organic chemistry bond, a carbon doubly bonded to oxygen. And this thing is called a carbonyl group. So this provides functionality to different organic molecules. So this is how we show it. It's trying to show that it's above. There's definitely a bond still here. That's the single bond. And then this is the double bond. And that's how it's above the bond. Okay. See you on Wednesday. Right?
What? Oh, Memorial.
Don't come here on Monday. Nobody will be here. Close will be locked.
What am I gonna do? Oh, that's sounding.
With some propane. And then you can tell everybody where propane comes from. They'll use some kerosene.
Lucky. Spend my weekend cutting down the tree.
I'm gonna reattach the HVAC system in my house.
My job isn't gonna be so bad.